Okay, let's start. Good morning.
Good morning.
Hey, stand up, stand up. Hey, how are you doing?
Fine.
How are you doing?
Marvelous.
How are you doing?
Marvelous.
Okay. Okay. Today we're going to talk about I/O buffers. How many of you have experience to put I/O buffers on your schematic? No. So you haven't experienced anything about I/O buffers. And maybe for now, all of you design a parser. In the end, after design, you simulate layout, LS, DLC, and everything is fine. But in the future, you will design a real team. And in real team, the team have to communicate with other side of the world. For that, you put I/O buffers. And at that point, you will make mistake. And actually, I/O buffer, this is the most of mistakes happens in I/O buffers. So I'm doing teachers for 7 years, and I got many questions, or I am consulted from students that they say my chip doesn't work. So please take a look. And when I took a look at the design, most of the cases they have mistakes related to I/O buffers. So this is very important. And usually in textbook, most of textbooks describe about core design And most of you are interested in designing core circuit. But this is very dangerous point, and most of mistakes come on I/O buffers. So you have to know about I/O buffers. And this is the illustration of chip-to-chip communications. So let's say the chip is assembled on a package. So here's the chip. This is the circuit, and there's the I/O pad, and this is inside of the package. And we have to communicate from the signal from the core circuit goes into the I/O buffers on the pad, bonding wire, lead frame, and line on the PCB board, and then the pin and bonding wire, I/O buffer, and input buffer. So this signal, this line is on the schematic. We just put lines, but this line and these lines are quite different because this line is about centimeter world, or sometimes tens or meters world. On the other hand, this line is in micrometers. So the physics are quite different. Of course, both of them are ruled by Maxwell equations, but the dominant cause of the physics is quite different in this micrometer world and centimeter world. And this is a picture. This is a Japanese coin. The diameter is 1 centimeter. And so this is about 1 centimeter, and the tip is about millimeter. And this is the bonding wire, and this is the link. And we have, there are many kind of packages. And in this picture, I use ceramic QFP package, and this is a plastic SOP package. But anyway, there's a line, wire here to here, and the wire always comes with inductance. Of course, wire always comes with resistance and always comes with capacitance. And there is resistance from here to here, and also there is capacitance between wire to wires. However, usually the bonding wires, these are relatively thick, so the resistivity is smaller. So usually we can ignore the resistance from here to here. And also, the distance between wire to wire are relatively long compared with inside of the tip. Inside of the tip, the distance is less than microns. But in this case, the distance is millimeter. So the capacitance are also ignored. But in this case, the length from here to here is very long. So in this case, we have to pay attention for inductance. And rule of thumb is 1 millimeter wire comes with 1 nanohenry inductance. So in this case, this is about 1 centimeter, so this is about 5 millimeters. So we have 5 nanohenry inductance per wire. And this nanohenry inductance causes noise, which will make us very digital. And we have to use pad. In the internal circuit and output of the world, we have to have, anyway, we have to have some connections. And there's a wire here, so we have to say this is the pad. This is the window to communication from outside world and inside of it. So here is the pad illustrations. And in a long time ago, the pad size is larger, but the process technology advances and transistor size shrink and shrink and shrink, and also pad size are also shrink. And usually in the advanced technology, we often use 60 micrometer pad. The pad pitch is about 60 micron, 150 micron, 40 micron, or something like that. And this is the window for the communication from the inside of the chip to the outside world. And so the pad itself is composed of metal, so usually aluminum wire or copper. And we usually have passivation layers to protect the transistors. So this is usually a glass coating. But when we have glass coating on the pad, we cannot communicate. So in order to the electrical signal going out or going into, we have a passivation window. And in most of chips, the paths are aligned around the side of the chip like this. And in some chip like memories, there is a pad on the center of the chip. And sometimes there is an array of pad windows all over the chip. But in most common alignment is something like this. And this slide shows a cross section of pad. Here's a silicon substrate, and on top of the surface there is a transistors. And the transistors, there is a metal wires, metal 1, 2, 3, 4, 5, 6, and 10. And as I told you, there is a glass coating on the surface of the chip in order to protect the inside of this chip from, for example, from dust or from water or something like that. And there is a window for communications. And the communication usually going through the bonding wire, which usually composed of road line. We use road. And there are two kinds of paths: the digital path and RF path. And most of case we use digital path. The digital part use the all metal layers like this. On the other hand, RF pads use only topmost metal layers. The difference is the digital part has large capacitance here between the pad and the substrate. But this is very robust. And the RF pad, we have only topmost metal layers, so we have less capacitance. However, this type of structure are easily blocked like this. So in order to avoid this, we often use this structure. But however, we have heavy capacitance. And usually, this capacitance is about 1 picofarad. And this capacitance is large, about 150 farad. But it's easy to grow, so we don't want to use it. Or quality control office does not allow us to use this pad. And this 1 picofarad is really large. As I told you, the wire here has about 10 farad. Compared with 10 farad, we have picofarad capacity. So that means if you use very small inverters, it's takes very long time to send signals in order to charge and recharge the capacitors. So for I/O buffers, we have to use large inverters in order to communicate in fast signal transmissions to charge and discharge picofarad capacitors. And again, it says 1 millimeter wire comes with 1 non-Henry inductance. And you would understand if you have simulations that, let's say you, for example, when you simulate this, and usually you use ideal power supply. But if you put induct 1 nanohenry inductance on the power supply and simulate it, the power supply will bounce. And for example, let's say the VDD is 1 volt, and once you put 1 nanohenry inductance, you will have 0.1 volt or 0.2 volt noise on the power supply line, and which will cause errors on the chip operations. So we don't want to have this large inductance. So for that, we often use flip chip bonding. That means on I/O buffers, usually we put bonding wires, and wires connect to from patch to the other side of the board. But we put ball down like this. This is process technologies. We put this kind of ball down here and directly attached to PCB board, so that we have less inductance, so we can provide clean power supply or clean signals. And next technique is multi-chip system in package. And again, in this case, we have to put wires and lead frames, which we don't have. And when, for example, we have CPU and memories, and CPU and memory have to communicate each other. At that time, it is difficult to drive non-Henry inductance or the picofarad capacitance we don't like. But in that case, we use this kind of structure. For example, there are many cases there is a memory on CPU. And this is called multi-chip or multi-chip package or system in package. And inside of the chip, inside of the package, we have a bonding wire like this. So that the bonding wire can be short. So that means short wire means less inductance and easy to transfer, easy to transform the signal. And but for these structures, the wiring techniques are very complicated. So there is some kind of regulation or cost, the limitations, the number of paths on the first chip, or number of paths on the second chip, and number of paths on the third chip. So before doing this, we have to consult with assembly department if this is possible or not. And also, the top chip should be smaller than the bottom chip. So by using this multi chip package, we can avoid long chip-to-chip communications. But anyway, we have to communicate with chip another side of the world. For example, if we have the CPU and memories are integrated on the same package, but still they have to communicate with parties or SSD and other side of the world like GPU. So anyway, we have to communicate chip to chip through PCB board. And for the communication on the PCB board, we have another problem. Here. It is called transmission line. So let's say we have input here, and this is a chip. This is a chip. And what this is PCB board wires, and this is the receiver chip. And the output impedance of the sender side is RS. And input impedance of the receiver side is RL. And there's a long wire. And let's say we have V0, like this kind of voltage is applied on input. So in this case, how many current flows? How many current flows? Three. No limitations. So we have RL here, RS here, and V0 here. How many currents? Let's say the long wire, the impedance, when you measure the wire impedance by a digital tester, it says 0. If the digital tester says it is 0, how many current flows? RL, RS, and V0, that means I equals V0 over RS plus I. Okay. However, this is a very long wire. If this is a very long wire, and this signal does not know there is a RL termination, because this wire is very long, what happens? After a long time, ultimately, the I0 would become this one. But as the first time when this voltage comes into this wire, how do they know this is RL? Maybe he doesn't know the wire is terminated by RL. So how many currents is going into this wire? And usually the wire, as I told you, wire always comes with inductance, capacitance, and resistance. So let's assume the DC impedance is 0. That means the resistance is 0. So there is inductance and capacitance. And here we ignore resistance. So in this case, and this current sees that this kind of LNC ladders, and it is said that the Z0. And Z0 is defined by square root of L over C. And we call this characteristic impedance of wires. So all the wires have characteristic impedance, even though it is the wires between inverter and inverter. It has characteristic impedance. And also there's a long line, if the line has characteristic impedance. And this line has characteristic impedance, and this line also has characteristic impedance. And we call this characteristic impedance, and we usually use Z0. And as you may know, you see L over C. So usually L is expressed as J omega L. And C's are also 1 over J omega C. So both of them has an imaginary part of impedance for AC signals, but Z0 has only real one. And this voltage sees that there is this voltage assumes there is a Z0 terminations. So when T first come in, the first current is expressed by RS plus Z0 over V. And also the V1 is divided and the V0 divided by RS and V0. So V1 is becoming like this. So this voltage comes into the line assuming that there is a V0 termination. And here the important thing is this is D0, so it assumes D0 terminations. But when we measure a resistance by digital testers like here and here, the digital tester says this is 0. So here we have to consider about the DC resistance and AC resistance. For DC resistance, it sees only resistance. And for AC, it sees this one. So, for AC signals, and AC signal means this step change means AC. So this step change feels that there is a V0 impedance. So the first input, like the current is becoming like this, and the voltage is becoming like this. And this assumes we have V0 terminations. But when he comes to here, he assumes there is V0 termination, but actually this is VL, not V0. So here, he finds that he made mistakes. So part of signals goes into the load, and part of signals are reflected and going back. And so the reflectivity is defined by gamma L. And after gamma L, we have the backward. So here, this says forward going, so we denote M. Forward going and backward going, so I say I1 B backward. So backward going wave, the amplitude of backward going wave is IF times gamma L. So this is the reflective. And inside of this, transmission lines, this signals also assumes that there is a Z zero termination at this time. So this signal goes into here and assuming that there is the zero termination. But he finds that the termination impedance is the S, not the zero. So part of it going into here and part of the and again and again and again, and in the end there is no reflection. So here, the first thing they come into assuming that they have the zero termination, but find that this is not supposed to like that. This is our L. So we have reflection and reflection and reflections. And this is what happens at the end of the long while. So, and reflectivity is defined like dl plus d0 by dl minus d0. This is the reflectivity domain. So once you know d0 and dl, you can calculate the reflectivity of gamma. So, and also, it takes time to travel from here to here. So this says that this is the sender side and the receiver side, and y-axis shows time. So at time 0, there's an incident voltage. And this incident voltage going to the receiver side as time goes. And at the time t, it's arrived at the end of the wires. And part of them goes through the load, and some of them reflect. And after reflected signals, it goes through the transmission lines and arrive at the sender side, and part of them goes into the impedance and part of them are reflected. And reflection, 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 and in the end, this reflected signal is becoming zero. And the reflectivity is defined by gamma L. So the amount of the current going into the load is defined like 1 minus gamma. So as we can see that the reflectivity is coming like this. So when the load impedance equals the characteristic impedance, there's no reflection. And we call this matched termination. So again, what happens when we measure the voltage at this point? What happens? When both sender side and receiver side has larger resistance compared with characteristic impedance. So this means that when the load impedance is larger than characteristic impedance, the reflectivity becomes plus. And if the load impedance is smaller than characteristic impedance, the reflectivity becomes minus. So let's say both of them are larger than the system, the characteristic impedance. In this case, let's say there is an incident wave here at time 0. And it takes time to go from here to here, and it takes time tp. At time tp, finally, the signal comes here and it has voltage. And first of all, the voltage here is, for example, V1 volt. And at this end, part of them reflects. And after the reflection, it becomes a backward going wave. So we say this is V1. And here, the voltage is added up. The voltage at here is forward going wave plus backward going wave. So the voltage here becomes fast forward going and backward going wave and voltage. And after this backward going wave, it takes 2 TP and come back. And so it takes 2 TP to come back and that voltage is added. And then after 2 TP, add up and add up and add up. And finally, getting into the steady state. And when the single size impedance is smaller than characteristic impedance, and the receiver side has larger resistance. So reflectivity at this point is plus and at this point is minus. In this case, at TE we have forward and fast forward and fast backward. And this first backward is reflected minus. So this wave is coming into minus and comes up to here. So the second forward going is becoming minus. And minus is reflected by plus, so that means the backward are also minus. And this minus going wave is then reflected and come back. So in this case, the voltage at here will also. And in the same way, when there is a large sender side and smaller receiver side, it oscillates. And most of them are smaller than the characteristic impedance. So when you measure the long wire, you sometimes have this kind of voltage waveform, and sometimes it oscillates. That means it depends on the input impedance on the receiver side and output impedance on the sender side. So, and it happens when we have very long wires. Any questions? So let's say we have a wire inside of the chip, and we have wires, very small wires between inverters. And we say we only consider capacitance here. But actually, all wires always come with inductance and capacitance and resistance. And in this case, let's say we ignore resistance. So the wire between inverters also have L and C, kind of like this. And the output impedance is, because this is kilo, so this is larger than the characteristic impedance of the wire. And the input impedance is almost infinity. So in this case, we have reflection and reflection and reflection. values, but the time here is proportional to the length of the wire. So in centimeter or meter wires, it takes picosecond. It takes about nanosecond. But in this micron wires, it takes only femtosecond. So in femtosecond, it's reflection, and finally arriving to the steady state. So in this kind of short wires, we can ignore the error and we can consider that this has only C. But actually, we can say that we have error and there is many reflection, and in the end it's going into a steady state. But the time is so short that we can ignore it. So every wire is a transmission line, and short wires can be treated as blunt elements. And this is the simple approximation of the transmission line. And here, so the short line can be approximated as only one capacitance. And long wire, we have to consider it as a transmission line, and we have to consider L and the reflections. And what is the boundary? So many people say many boundaries, but my boundary condition is lambda over 6. So usually electromagnetic signals, speed of electromagnetic signal is the same as speed of light. That means the speed of the electromagnetic signal is about 3 times 10 to 8 meters per second. So in 1 second, it goes to 30 centimeters in 1 second. That means for 1 gigahertz signals, the wavelength is 30 centimeters. So 1 gigahertz signal has a wavelength of 30 centimeters. So in this case, lambda is 30 centimeters divided by 6 in 5 centimeters. So if you communicate in 1 gigahertz, over 5 centimeters, we have to consider it as a transmission line, and we have to consider about reflections. And if less than 5 centimeters, we can treat it as only a blunt capacitance in vacuum. So in PCB boards, usually we use FR4, whose permittivity is about 4. So the wavelength is becoming half. So on PCB board, and your communication frequency is 1 gigahertz. The wires less than 3 centimeters, you can ignore the reflections and you can treat it as capacitance for 1 gigahertz. So if you want to communicate using 10 gigahertz, it becomes shorter, and less it's about millimeters. So 100 gigahertz is very short. So most of the case, you have to treat it as a transmission line, and you have to calculate the reflections and simulate by using L and C. And it takes time to simulate, so it will cause big problems. And usually in standards, the Z0, we have standards. And usually the standard says D0 is 50 ohm. And sure why we use 50. And for example, for television antenna, we use 75 ohms systemic characteristics. So the analog TV set, we put some kind of wires which has whose characteristic impedance is 75. And this cable may be 50. Actually, I'm not sure about it. But most of the case we use 50 ohm characteristic impedance. And we often call it system impedance. So system impedance is about 50 ohm also. For example, so for when you are designing our circuit, in our circuits world, 50 ohm is a standard. And in order to avoid the reflections, because reflections will oscillate and it takes time to settle the signals, so it takes time to wait until settle to judge if this is 1 or 0. So we usually have matched terminations. So when matched termination, after TP, we have stable signals when matched, because there is no reflections. So matched termination will give us more fast bit rate of communications. So we want to have matched termination. And so there's many kind of matched termination too. And usually for low speed, that means the transmission line length is less than 1/6 of the wavelength. So for 1 gigahertz signals, it is about 6 centimeters. For 100 megahertz, it becomes 30 centimeters. For 10 megahertz, 3 meters. So your communication speed is about, let's say, your communication speed is 10 megahertz, 10 megabps. And the communication length is from here to here. We don't have to care about so much. But we want to communicate 1 gigahertz from here to here. We have to have matched termination. So there's many kind of termination. But one is no termination, but we can use it only for low bit rate signals or low bit rate. And the parallel termination here, we have RT, which is terminated ground. And RT is equal to D0, we call it matched terminations. And in most of high-speed measurements devices like oscilloscope, spectrum analyzers, maybe you will use in the future. For oscilloscope, the input impedance is usually 50 ohm. So this termination are very compatible with high-speed measurement device. And in this case, because this is the 50 ohm relatively small, so let's say the output impedance is 50 ohm and supply voltage is really, and 50 ohm and 50 ohm, so the output voltage here is only half. So high signal is not be, this might be a problem. But anyway, in order to avoid the reflections, we use this kind of termination very often. This is called parallel termination. And another one is step-down termination lines. So we use another supply voltage here and parallel, the T1 and T2 parallel of these is becoming big. So that we can control this DC voltage, we can control the high level of this one. And that's sometimes good for receiver side. For example, when we receive the signal by normal inverters, logical threshold is half VDD. So in this case, when the output impedance is equal to 0, the high signal becomes half VDD. So inverter sometimes misunderstand that signal is not high. But in this case, when you apply higher voltage here, we can control the DC voltage here, so it is easy for the receiver side to judge this is high or not. Another termination is series termination here. So that means there is no termination here. And in this case, the output impedance plus the RS becomes 50. So in this case, when you output the signal for, let's say, V1, send V1 here, and this is 50 ohm plus 50 ohm. In this case, transmission so this has a reflectivity at 1. So after the reflection, it will have VDD voltage. And after the reflection, because this side is matched termination, so there is no multiple reflections, only reflect at here and go into like this, and no multiple reflection. And it sometimes works fine. And also we can have AC termination here. So when we put large C, so large C means it is open for DC and it is short for AC. So this case for AC signals fills only RT, so match termination. And for DC signals it is open, so there's no DC current flows. And this goes off. And for differential terminations, and we often send the data and data bar. And for data and data bar case, let's say we have 50 ohm to virtual ground and 50 ohm to ground. And because both of these signals are always it balances, always balances. So at the center point is virtual ground. Because the center point does not change even though high to low or low to high. So the center point is always ground, is stable, so we can consider it this is the virtual ground. So 50 ohm plus 50 ohm equals 100 ohms. Put 100 ohms here can have much termination for differential signals. So these three are the major termination techniques: no termination, forward termination, terminal, series, AC, and differential. And other things is that we have to consider the signal level. That means chip A wants to stop in 1 volt and chip 2 wants to stop in 3.3 volts. They cannot connect. So we have to use common language for the chip. And this is the types of common languages. And LVDS, the high voltage is this and low voltage is this. And CUDCL, LV, there are many types of common language in common voltage. So when you buy a chip and communicate with that chip, we have to talk his chip. We have to talk in this chip's language. And if you design for the sender side and receiver side by yourself, you can use your own language. So you can decide the high voltage and low voltage. But if you talk with other chips, you have to follow this language. And other programs, there are many kinds of programs, and the other program is ESP. I'm not sure about this happens in Vietnam, but in Japan we have very cold winter. So we wear sweater, and when we wear sweater, and in winter it is very dry. So in dry atmosphere and in cold and we wear sweaters, and sweater will make charge on our body. So when we put, for example, when we put doors, we have electric discharge. It happens in Japan. I'm not sure if you experience that in Vietnam, but in Japan we have that. But anyway, our body accidentally has charge, and in charged person put LSI. The charge is getting into the LSI and the LSI breaks, and it is called electrostatic discharge or ESD. So we don't want chips to be broken even if we touch. And there are many kind of ESD models. So mainly we think three types of ESD charge. One is human body, that is charged human body touch DLC. And machine model, that means machines, charged machines touch. And charged device model is the chip itself is charged and grounded machine touch. But anyway, it happens the chip grows, so we have to insert protection circuit on either one. And for human body models, usually we charge hundreds of volts. That means we sometimes charge about 100 volts. And we have also resistance here. So that means the 100 volts charge capacitance connected to human body resistance. And so this RC circuit will attach to ground. And machine model, usually machine assumes to have no resistance. So the charge capacitance directly comes to LSI. And also charge LSI are directly touched by grounded machines. And ESD protection circuit, we have to embed ESD protection circuits on I-bar. And basically, the basic idea is the charge should be going to power supply line or go into ground line, so that the charge does not go into the circuit to break. And the basic idea is when we put off transistors. So when NMOS gate is grounded, this is off. Then PMOS gate VDD is on. And we have resistance like this. So in this case, let's say we have a very high voltage inside. Let's say VDD is 1 volt and this is 100 volt. For 100 volt, for PMOS, 100 volt here. So this side will become source. And 100 volt and gate is applied 1 volt. That means from 100 to 1 volt, so the PMOS is on. So when high voltage applies, PMOS is on and goes into the DP. When minus charge applies, minus 100 volt. So in this case, this side, this node is applied minus 100 volt. So compared with minus 100 volt, the ground is higher than minus 100. So the NMOS becomes on, and minus charge is going into this ground. This is called ESD protection diodes. It is called diode. So, and this resistance. So this is high voltage. So once it goes through the resistance, it has voltage drop. And high voltage is not applied inside. So we put this resistance and this resistance to protect inside of the and also these resistance will protect these diodes. And from ESP protection point of view, we want to put large resistance here. But large resistance will disturb the communication. So for high-speed communications, we don't want to put it. But from ESP point of view, we want to put large resistance. So we have to compromise. There's a trade between the ESP protection and communication speed. And how to implement the ESP protection circuit? At first, we are considering about this resistance. And this resistance, we have transistors. And let's say we have city side on the gate and city side on the source and drain. And if we remove city side, it has resistance. So we put city side protection layers here, so that there is no city side on the surface. So we can have resistance like this. And also for these resistors, we usually use this kind of multi-field, the source drain regions. And in this case also we remove the series side. Yeah, remove the series side so that we can have a resistance. Or we sometimes have a gate poly as a resistance. Transition. We could use gate poly without series. So anyway, for ESP, we use series side protection layer to prevent the resistance to protect ESP. So we have trade-off related to ESP. So once we have a larger, we have high ESP tolerance plus speed. And these resistors, when we have a larger resistance here, it will protect these diodes, but larger resistance will let this input charge into the internal circuit and internal circuit later. And if we use less resistance here, the charge is going into here, but this diode will break. So it's sometimes very difficult to decide how many resistance we use. And so let's say we have output buffer here or input buffer. And from output output buffers, this node is PM junction. And for input buffers, the path is connected to gate. And gate oxide is easy to break compared with PM junction. So output buffer has more strong rather than input buffer in terms of ESD. The gate is weaker than source drain, so it's buffer. And also, let's say we have 50 ohm termination like this in order to avoid reflections. When we have 50 ohm impedance to ground, so the ESD charge will easily go through this impedance. So the 50 ohm termination will plug down resistors and have ESD protection. But in here I have to say that output buffer is more strong and input buffer is weak. So we have to protect input buffer rather than output buffer. And SOI, how people design SOI? This is a cross section of normal transistors, and this is a cross section of SOI, which is silicon on insulator, and it is called next generation transistors. So ST Micron utilize, ST Micron commercialize SOI process for 28 nanometer. And in SOI, there is a junction capacitance between drain and substrate, and junction capacitance will degrade the performance. And because this is a very low size, so there's less capacitance here. So this will have higher performance in terms of switching. So this is it is said that this is the next generation transistors, and RDM are using SOI and ST Micron using SOI. But the weak point of SOI is this is weak against ESD. Because for ESD protection circuits, the ESD current going into here, and this will, the charge can go into substrate. But for SOI, there is no current into the substrate, and the current coming into drain is always coming into the channel. And this is a large current, so it will break the transistors. So SOI is weak against ESD, and this ESD is the main cause that they cannot commercialize SOI process. And so there are many kinds of I/O buffers, and in selection of I/O buffers, you will make mistake and your chip does not. It often happens. Maybe more than half of mistakes is mistake of selection of I/O buffers. This is very important. And we have many kinds of I/O buffers, and this is the CMOS buffers. The sender side is just inverters, and the receiver side is also inverters. Both of them have ESD inverters. In this case, the high and low signal have VDD and drum. And again, the path has picofarad. So in order to drive picofarad capacitors, these inverters should be large, very large. Very large means, for example, for recently I use 0.18 micron. For 0.18 micron, the transistor size is about 100 micron. And for 28 micron technology, the transistor size is about several tens of micron. So it is about 100 times larger than the transistors used in the device. So you may use 100 or more than 100 larger transistors for microphones in order to drive people follow devices. But anyway, this is inverters. Inverters and inverters. And in this case, as you can see, we have no termination. So no termination, we can use this only for low data. And other one is tri-state buffers. And tri-state means output high or low or high Z or output high or low or all. So that means when both of these transistors are off, it means high impedance from the same point. So for high Z, this is seen from here, it is called open. So when open, this voltage is unstable. So when this voltage is unstable, and let's say this is becoming half VDD, and half VDD lets these transistors are partially on, and there is current from VDD to ground, and it will consume our power, which we don't like. So for open output, we put large resistance. So large resistance means it can be ignored. It is large, too large compared with all resistance on this transistor. So it can be ignored if this output buffer output high or low. And it works only when it is open. When it's open, this resistance will cool down this load and cool down to this load to us load. So that we will not have through current from VDD. So for high Z outputs, if possible, and in that case, we have to cool down transistors. And when this is connected to VDD, we call it pull up resistor. Another one is built-in resistor. In order to avoid the reflection, we indeed the termination resistance connected to ground. So usually it's 50 ohm. So because there's a 50 ohm, the ESD charge is easily goes into ground. So in this case, we don't use ESD protection circuit on it. And for center side, we want to put ESD. But for high speed communication, we don't want to put ESD. And for center side, this is the output buffer. And again, output buffer is connected to PN junction to the pad. So this is strong. So sometimes we don't need ESD protection circuit for output buffer. So for high speed, we remove ESD protection. Here we put only off transistors here. We remove resistance because this is strong. And for input buffer, usually it is weak, but we have termination resistance and it works as resistance protection. And 4, and this is called open drain. That means the drain terminal is open side, it has termination resistance connected to VDD. So that's when this is on, the current going from here to here and out to flow. And when this is off, this is off, this is high, pull up to high, so this becomes high. So on and off means low and high. So he can just, this is high off. And this is the source follower. And N constant connected to VDD, and so the output voltage is a copy of it. And we often use this for analog circuits output, analog signal. And for analog signal, we, for CMOS, in this case, we will output only VDD formula, high and low. We have two signals, high or low, two levels. But for analog signals, we want to send analog waveforms. And in such case, we use source follower that copies this voltage into output. And in this case, we want to use this. Well, we have the termination resistance here. So, and other line buffer is just only analog input and output. So we use this kind of voltage circuit, but we have ESD voltage. We use this, for example, we want to have bias voltage. When we say op-amp, and we have bias voltage for current source. In such case, we use this kind of input and output components just for bias. And sometimes VDD, we have multiple VDDs, VDD1 and VDD2. And in such case, we sometimes put diode for ESP. Right? And this is the final topic, the powering. Usually we put internal circuit here, and we align the output path like this, and we align the input and output buffers like this. And power and ground, because the output buffer has to drive picofarad or 100 picofarad, so it consumes large powers. And consume large powers means it will generate big noise. So we want to divide the power line for I/O and power line for internal circuit in order to cross talk between the I/O and internal circuit. So like this, we often use I/O power ring. And this is the ring for power VDD for I/O and ground for I/O. So power supply only for I/O and surrounding internal circuit. And usually we design the I/O circuit. There are many types of I/O circuit, but we design in the same size, so that we can easily replace this is VDD and this is ground, this is output and this is in. We just replace the cell so that we can match with this power link, so that we can easily change our design. And for this power ring, VDD ring and ground ring, and sometimes we put ground inside, or sometimes VDD inside, and it's depends on people. And for my case, I I put ground inside and VDD outside. But other one use VDD inside and ground outside. So I have my own reason and he has his own reason. But anyway, you have to find your own reason and you can use your own way. Anyone which one is okay, but someone will ask you why you use that, and you have to explain that. And I use ground. And in distributions, when we assign pins, which pin should be ground and which pin should be signal, which one is internal ground, and we have to decide. And there are some rules to obey. The first rule is, and VDD and ground line should be close, because we have inductance on the wire, and we want to reduce the inductance to reduce the noise. And actually, I told you that the 1 millimeter wire has 1 ampere. But this is just approximation. And the inductance is decided by the current loop areas. If you use wider loop, it will have a large inductance. If you use small loop, you will have small inductance. So VDD and ground should small in order to reduce the loop area and to reduce the inductance. So this layer is better. Sometimes we want to reduce inductance, so we use multiple VDD and multiple ground. And let's say one pin have 1 ampere, so 2 parallel pin means 0.5 ampere. So we want to use multiple pins to reduce the impedance. So even in such case, someone puts VBGG. And VGB is better compared with VBGG. Because VBGG means there is a loop here. But VGBG means there is a parallel connected loop. So you will have smaller inductance. So smaller inductance means smaller noise. So VGBG is better than VBG. And another rule is that other signals or high-speed signals are sandwiched by ground. That means, for example, in this case, let's say this S1, S0 is very important signals, important analog signals. And in this case, the adjacent wires can have crosstalk to the important signals, which we don't like. So in this case, the important signals are sandwiched by ground, so that the other signals are not crosstalk to the important signals. And this ground line will protect the crosstalk. And the other rule is symmetry. You have to consider symmetry. For example, the data and data bar. And data and data bar signals want to come at the same time. But as I told you, it takes time to travel into the wires. So when the wire length is defined at distances, the arrival time is different, and it will cause noise. So in order to have a symmetry data and data bar, usually the chips and package a symmetry at this point over these or at these. So you have to think about the symmetry of the structures and take care of it. So when symmetry signal, this and this is not true and this and this. That's all in English. Most of the case, we have to do ESP even for our partners. And basically, we will put ESP even for our partners. And actually, ESP has three models: human body, machine model, and charge device model. And as long as the chip passed this test, it is okay. So, and basically we have to put this. But for high-speed signals, we don't want to put resistors. So for high-speed signals, or for example, RF signals, RF input and output, in that case, we want to remove the ESP, because if there is a ESP, we cannot meet the specifications. In such case, we remove that and test ESP and see if it passes or fails. And if it passes, it's okay. And there is a large chance to pass even though no ESP, because this is argument. But even if it fails, sometimes we can ask quality assurance department that this thing should not have ESP. This is weak against ESP, but this is very important, and this will not meet performance specification if we have to have ESP. So we will negotiate with quality assurance, and we will negotiate with customers if this thing is okay that this has weak ESP. In many cases, they know about that. The RF thing is difficult to have ESP. So sometimes, in that case, on the specification sheet says this is RF thing, and you have to take much care many chances because this has no ESP. And for input buffers, these types of input buffers have to have ESP protection because this is directly connected to the gate, and it is not. This is weak against ESP. But for high speed and RF circuit, for high speed and RF circuits, input buffer always have termination resistance, 50 ohm termination resistance. So in this case, this is strong against ESP protection. Strong against ESP. So when you send this to quality assurance and say, let's test it, maybe it will pass. But anyway, even though it fails, you have to negotiate with quality assurance and customers and say this and this things are not as easy. So they find something and change it.
In case that we design a battery chip, the chip operated by obtain RF signal. So, for example, when we design a battery chip, battery chip,
Passive.
yes,
Passive. What do you mean passive?
This means that satellite RFID chip is operate when receive the RF signal.
Receiver.
Yes,
Okay.
it's receive the RF signal to operate. So do we need BSD to protect the chip?
Yeah. So that's the same question. For receivers usually have termination resistance. So in this case, it has high immunity against ESD. So it often happens that it will pass ESD test, even though it does not have ESD protection circuit, because this termination register works as ESD protection circuit. And if it fails, you will negotiate with customers and quality assurance. Okay.
We'll say monitor about the RF, ESD, especially the, for example, PA or the power amplifier. Because I saw that the many power amplifier, they say that cannot touch hand the chip, so I think.
For power amplifier, we have coil here, coil, and we have capacitance, and we have coil here for the sender side, and receiver side also on the receiver side. So there's antenna outside. So this is mixture. So coil and internal capacitance may have resonance at your desired frequency. So when you put this kind of ESD capacitance, ESD protection circuit, it's and let's say there's no resistance. Here, first we ignore resistance. When we ignore resistance, the ESD protection circuits work as capacitance. So when you put L and the parasitic capacitance, L and C resonance frequency is matched with the target frequency. So sometimes power amplifier put intentional circuits to adjust the resonance frequency. So you can utilize the ESD protection circuit as adjusting C. And if the ESD protection circuit C is much larger than your desired capacitance, you have to reduce you cannot put the ESD protection and see that this is already so effective. Yes.
We want to ask about characteristics that we see to receive
Usually LW is frequency and C is also frequency. So these two are frequency. Now let's say we have R here, and R here or conductance here will induce the complex number for D0. And if there is a R or conductance, the D0 has is become complex number and it has frequency dependence. But when we ignore the resistance and conductance, D0 is frequency independent. And also case, for example, for RF cable, we can ignore RF conductance. So RF cables are frequency independent and it always be fixed. Any other questions? Okay, let's take 10 minutes break. 10 minutes.